Let's investigate the Transmon Hamiltonian. This has applications in quantum computing, specifically in the study of superconducting qubits. The concepts in this video will build upon the ideas that I covered in the quantum LC circuit videos, which are also in the quantum mechanics playlist. In this video, I'm going to begin by writing down the Lagrangian for the Transmon. And we're going to see some similarities to the Lagrangian for the quantum LC circuit. So let's begin. Fancy L is going to denote the Lagrangian. And the Lagrangian will consist of two terms over here. The first term is going to be like the kinetic energy, and the second term is going to be like the potential energy. So we have C capital phi dot squared on 2 plus I naught capital phi naught on 2 pi times cosine of 2 pi phi over phi naught. So phi, this capital phi over here, denotes the flux. And this is the coordinate that we're using to describe this system. So this is a device. It's a superconducting quantum device. And the coordinate that is describing the state of this device is phi. So in the Lagrangian, we have phi and phi dot. This is analogous to the velocity. We're taking the time derivative of the coordinate. That is why this term is called the kinetic energy, and this term is called the potential energy. The kinetic energy depends on the velocity, and the potential energy depends on the coordinate. And what you might also notice is that inside this cosine, we have 2 pi over phi naught. Phi naught is just a constant. And on the outside, we have a reciprocal. Now that's going to become important when we take derivatives of this. So you'll see that later in the video. Now what I want to do is just have a look at the canonically conjugate coordinate, which is actually going to be charge. So charge is going to be denoted by capital Q. And it is equal to the partial derivative with respect to phi dot of the Lagrangian. So let's look at the Lagrangian and see how we can differentiate with respect to phi dot. There is only phi dot in this term. There is no phi dot appearing in this term. So when we use the power rule and differentiate this kinetic energy term, that's going to give us C phi dot. And this is the canonically conjugate coordinate. So you can think of this like momentum. This is analogous to momentum. And this is analogous to velocity. This is just like momentum is mass times velocity. So capital C over here, that's the capacitance of the circuit. The capacitance is playing the role of the mass. So now what I want to do is write down the Euler-Lagrange equation. So the Euler-Lagrange equation has a time derivative of this quantity, the partial derivative with respect to phi dot of the Lagrangian. And then we also have a term involving the derivative with respect to phi. So we have the partial derivative with respect to phi of the Lagrangian. And all of this is equal to 0. We can also move this guy to the other side of the equation. We can just add this term to both sides. So this is the Euler-Lagrange equation. And we already know what this thing in the brackets is over here. This quantity is the canonically conjugate coordinate, or the momentum. And in this case, the momentum is actually the charge. So it's important to remember in Lagrangian mechanics, the coordinate does not necessarily have to have units of position. And this canonically conjugate coordinate does not necessarily have to have units of momentum. In this case, they have units of flux and charge. So flux and charge play the role of position and momentum. So let's actually compute all of these derivatives and find the equation of motion. So we know what this is. It's just C times phi dot. And C times phi dot, if we take another time derivative, that's going to give us C phi double dot. So we have C phi double dot. This is kind of like mass times acceleration. What we're actually getting is the equivalent of Newton's second law of motion. We have mass times acceleration is equal to some kind of force. That is the equivalent version of this expression. And that's what the Euler-Lagrange equation actually gives us when we're dealing with mechanics. So let's have a look at this term now. We found what this term is. Let's have a look at this derivative. We need to differentiate with respect to phi. Phi does not appear over here. It only appears in this cosine. This is phi dot, and that's different. It's independent from phi. The velocity and the coordinate are not the same thing. So let's differentiate this expression over here. If we differentiate cosine, that's going to give us minus sine. But we already have a minus over here, so those two minuses are going to give us a plus. So we're going to get plus I naught sine of everything inside here, 2 pi capital phi over phi naught. And this is equal to 0. You might notice that a lot of these terms have disappeared. That's because of the chain rule. The chain rule allows us to take all of this stuff, the derivative of the inside, and move it to the outside. And we multiply that, and what we have is actually the reciprocal of this fraction. So this 2 pi cancels with this 2 pi, this phi naught cancels with this phi naught. That is why the Lagrangian was chosen to have this form. And that is why all of these constants appear in the front. So I began with the Lagrangian, but usually you actually begin with the equation of motion. That is what this thing in red is over here. This is the equation of motion for the transmon. We have a coordinate phi, and we know how that evolves with respect to time. This over here is inferred. So we infer the Lagrangian from this. We infer the Lagrangian by finding a kinetic energy term and a potential energy term. So this is actually kinetic minus potential. It's minus because this potential energy term already has a minus sign. So those two minus signs give us a plus. So implicitly, we have kinetic minus potential. Now, one thing I want to define over here is this phi naught. Phi naught can be thought of as the flux quantum. So phi naught is just a constant, and it is equal to Planck's constant over twice the charge of the electron. We're going to be seeing 2 times E, twice the charge of the electron, appearing very often in expressions when we're looking at superconducting quantum devices. That is because electrons come in pairs in superconductors, and those pairs are called Cooper pairs. So that is just a little physical insight, and that is why we have 2 times the charge of the electron over here. So anytime we see phi naught, that is just shorthand for all of these constants. These are fundamental constants, Planck's constant and the charge of the electron. Now what I want to do is find the Hamiltonian. The reason we started with the Lagrangian was to find the Hamiltonian. So how do we go from the Lagrangian to the Hamiltonian? Well, we do the Legendre transform. So I'll write down the Legendre transform. The Legendre transform has this form. We have the canonically conjugate coordinate, that's q. Then we have the velocity, which is phi dot. And then we subtract off the Lagrangian. Now, what are we going to get when we do this? We know what q is. Q is equal to c phi dot. In general, if you have a Lagrangian that has multiple terms that depend on phi dot, this is going to be a lot more complicated. Each of those terms that depend on phi dot are going to contribute a term into this canonically conjugate coordinate. But luckily for us, there is only one term, and we just use the power rule to differentiate it. So we have a very simple relationship between the quantities that are analogous to momentum and velocity. So that's very fortunate for the algebra over here. It's very simple algebra. So what we can do is we can substitute this q inside over here. So that's going to give us c phi dot squared, because we have 2 factors of phi dot. So we have c phi dot squared, and then we're going to subtract off c phi dot squared over 2. So that's a whole minus a half. That's just going to give us a half. So we're going to have c phi dot squared over 2. And that has a plus sign, because we have plus a whole minus a half. But this term over here is going to get subtracted. We're subtracting the Lagrangian off. So this plus is going to turn to a minus. So we're going to have minus I naught phi naught over 2 pi times cosine of 2 pi phi over phi naught. So this is the Hamiltonian written in terms of the coordinate and the velocity. We have phi and phi dot. So the only thing that has changed is the sign over here. Here we have a minus sign. Usually what happens is you have kinetic minus potential as the Lagrangian, and then the Hamiltonian has kinetic plus potential. But over here, we have the opposite of that. We have plus and then minus. Why is that occurring? Well, Well, that's because this potential energy function has a minus sign. So that minus sign is canceling the other minus sign. So just remember that this is implicitly minus cosine. And over here we have implicitly minus cosine. And that is why the signs are opposite of what they usually are. Now, the next thing I want to do is translate this Hamiltonian into quantum mechanics. So this is the reasoning. We reason with this as if this was a classical system, and then we translate it into quantum mechanics by promoting some of these quantities, some of these variables to operators. We turn them into operators and we put a little hat on top. So let me just manipulate this kinetic energy term a bit, and then we'll translate this into quantum mechanics. So the Hamiltonian operator in quantum mechanics is going to be 4 times E squared on 2C. So I'll show you in a moment why I'm doing this manipulation, times Q on 2E all squared. So this is the kinetic energy term. This is the same as this term over here. So what have I done? All I've done is I've substituted a Q in place of phi dot. So if we divide both sides of this equation by C, we get Q over C. So I can substitute Q over C in place of phi dot over here. That's going to give me Q squared over C squared, and one of those C's are going to cancel. So that's going to give me Q squared over 2C. And you can see Q squared over 2C over here. And I've also multiplied and divided by a factor of 2E all squared. We have 2E all squared down here, and we also have 2E all squared, and I've just squared that 2 and moved it outside over here. So this coefficient out the front, I'm actually going to call E sub C. So the capacitive energy. Another convention, which I used in previous videos, would have this 4 absorbed into this constant. So both conventions are commonly used. And every time I write down EC, I will tell you which convention I'm using. Is that 4 outside, or did I absorb the 4 into this definition? So this is the kinetic energy term. It is just like changing the kinetic energy and writing it in terms of velocity, and then writing it in terms of momentum. So it's just like 1/2 mv squared, and then p squared on 2m. So that is a common thing that we like to do. We like to change it from velocity to momentum, because momentum is a more natural quantity for Hamiltonian mechanics, and then that translates very nicely into quantum mechanics as well. Now, I also need to write this potential energy term, and I'm just going to leave it exactly the way it is. I naught phi naught over 2 pi cosine of 2 pi phi over phi naught. So that is exactly the same, but I also want to define this term out here. I want to define that as E sub j. Now, why am I using j to denote this? Well, it's because this potential energy term is actually associated with a Josephson junction. And that is a very important component to a transmon. So we have this energy over here, which is associated with a capacitor, and this energy, which is associated with a Josephson junction. And that is a very important device in superconducting quantum devices. So we have a Josephson junction and a capacitive term. And that's why we have EC and EJ. I also want to define new operators over here. But first, let me promote these guys to operators. So this H is the Hamiltonian operator. It has a hat on top. This charge over here is the operator for charge. And this flux over here is now the flux operator. So this phi naught is just a constant, and this is an operator. And now I want to define all of this stuff in the brackets over here as n hat. So this is little n hat. And all of this stuff in the brackets over here, I'm going to define that as lowercase phi hat. And this operator I'm going to call the phase. So this was the flux, and now that I've multiplied it by this constant, I'm going to call it the phase. So these guys are actually dimensionless operators. So we've taken out the dimensions. This charge has been divided by something that has units of charge. And this over here, this flux, has been divided by something that has units of flux. And we also have this 2 pi because we want to put this inside a cosine function. And that's why that 2 pi is there. So these are the new quantities that I defined. So I'll write that Hamiltonian out below. So this is what the Hamiltonian looks like now. We have the Hamiltonian operator is equal to 4 EC little n hat squared. Right, so we have this n over here, and we're squaring it. And then we want to subtract from that EJ cosine of the phase, little phi with a hat on top. So I want you to distinguish this capital phi with this lowercase phi. So capital phi still has dimensions of flux, but this guy does not have any dimensions because we've divided it by this factor over here. So these are dimensionless quantities. And that's very useful. It's very useful to deal with dimensionless quantities. We're writing it in terms of the natural units. And with this definition, I'm keeping that 4 outside. So this 4 is outside over here. I could also write this with an alternative definition by just moving this 4 into the constant, just absorbing it into a single constant. The next thing I want to do is I want to do a Taylor series approximation on this cosine. So I'm going to write that this is approximately equal to, I'm not going to touch this term over here. I'm just going to leave it the way it is. So this kinetic energy term. It's a quadratic term over here. And what I'm going to do is I'm just going to expand this cosine in terms of its Taylor series. So I'm still going to have EJ, that's that Josephson junction energy. And I'm going to turn this cosine into 1 minus phi hat squared on 2 plus phi hat to the power of 4 over 24. And I'll stop over here. We could add more terms if we wanted to. This is just the Taylor series approximation expanded up to the quartic term. So here we have a quadratic and a quartic term. The cosine function has a Taylor series that looks like this. We have alternating signs, plus, minus, and we're only looking at the even powers. And every time we see an even power, we're dividing by the factorial of that power. So 2 is actually 2 factorial, and 24 is 4 factorial. If I wanted to add more terms as well, then I would have phi to the power of 6 and phi to the power of 8. So all of those even powers would appear in this expansion. But I'm just going to cut it at this over here, truncating this series. Now, let me do some manipulation. This approximation is equal to, we still have that kinetic energy term, 4 EC n squared. But have a look at this quadratic term. Minus and a minus give us a plus. We get plus EJ on 2 phi squared. That's the quadratic term. And then we have a quartic term with a minus sign, minus EJ on 24 phi to the 4th. And there's also a constant term. You can see this constant term from the 1, minus EJ. Let's have a look at the terms in this Hamiltonian. This is an approximate form of the Transmon Hamiltonian. So we successfully derived this Transmon Hamiltonian from the Lagrangian. We began with the Lagrangian, we took the Legendre transform, and then we promoted these quantities to operators. We repackaged some of the constants, we got rid of the dimensions of these operators, we defined some new quantities, and this is what we have. We have a Hamiltonian for the Transmon. And now I've just expanded this out in the Taylor series approximation. And that's given us these terms. Have a look at these two terms over here. They're both quadratic. We have something that's quadratic in n and something that's quadratic in the phase. So both the charge and the phase have something that they're quadratic in. And that is exactly what you'd see in a quantum LC circuit. That's a quantum harmonic oscillator. So we have a quantum harmonic oscillator with some higher order corrections. So what is this term over here? This is a quartic term with some higher order corrections. And this term over here has no physical significance. This is just a constant. We can actually get rid of this constant by defining the potential energy differently. Instead of having cosine over here, we could have 1 minus the cosine. So this is actually minus cosine, and this is minus cosine. That's the potential energy. And we could just define 1 minus cosine, and then that constant is going to cancel out with this constant over here, and then we won't have a constant appearing over here. That has no physical significance. You're just shifting where you define 0 for the potential energy function. Now, can you see some parallels with the pendulum? There is another video in the quantum mechanics playlist where I discuss the pendulum. And the pendulum can also be approximated by a simple harmonic oscillator. But as you move further and further away, this quartic term becomes more dominant. So you have to consider the quartic term. So locally, very close to the minimum, it is a harmonic oscillator, but then you have that anharmonic behavior as you move away. So this is very important because one of the essential properties of this transmon that we desire is anharmonicity. We don't want the energy levels to be exactly the same. We don't want them to be evenly spaced. And that allows us to make an approximation where we can treat this transmon as a qubit, where we just have the ground state and the first excited state. So we have an energy difference between the lowest and the first excited state, and then the next two excited states. And that energy difference is actually different. So we have a small anharmonicity. So anharmonicity means it's not harmonic. So if we didn't have these terms, we would have a harmonic oscillator. That's exactly the same as an LC circuit. But now that we have to include this term into this expansion, it changes it and it makes it into an anharmonic oscillator. So that is some very fascinating stuff that we've discovered just by performing this Taylor series expansion. So EJ is actually playing the role of an inductive component. So this is behaving kind of like an inductor. But it's not quite an inductor because you have higher order corrections. So the next thing I want to do is I want to write down a very important relationship between these two variables. We have phi and n. And if we take the commutator of these guys, we get the imaginary unit I. This is just like the canonical commutation relation between position and momentum. But for position and momentum, we would have I h bar over here. But because we've gotten rid of all the units, we just have I. If instead of the phase and this normalized charge, we put in these capital letters, if we put in Q, and capital phi, we would have the same relationship as position and momentum. We would get I h bar. But that h bar disappears when we get rid of the units. You can see that if you multiply these guys together, what you actually get is something that has units of h bar. It has units of energy times time. So the next thing I want to do is I want to see what happens if we add a little shift to this n. So what happens if we take n and we do a little transformation? We say n gets shifted to n minus ng. So this over here, this is an operator and this is a constant. So we're just giving it a little shift. So what is the Hamiltonian going to look like if we give it a little shift? Well, it's going to look like this. We're going to have a Hamiltonian of this form. The kinetic energy term is going to change. We're going to have 4EC times this operator n minus ng all squared. And then we're going to subtract from that EJ cosine of the phase. So this is the new Hamiltonian with this little shift over here. So we've just shifted the charge. This is a little charge offset. You can think of it as an offset, and that is actually going to change some of the properties. So let's have a look at this Hamiltonian, and let's write it using the time-independent Schrodinger equation. So let's put this into the time-independent Schrodinger equation and see what we get. So I'll do that below. So first of all, let's write down the time-independent Schrodinger equation. So we have the Hamiltonian operator acting on one of the eigenstates. This is Dirac notation. That gives us an eigenvalue times this eigenstate. And another thing we can write down is if we want to express this in the phase basis, which is analogous to the position basis, we could write an eigenvalue equation for this phase operator. If it's acting on one of its eigenstates, it's the same as multiplying its eigenstate by an eigenvalue of phi. So this is just like the position operator, except we're not dealing with position over here, we're dealing with the phase. This is the superconducting phase. So now what I want to do is I want to act on this expression over here, the time-independent Schrodinger equation, with the phi bra. So we'll take the bra on the left-hand side and act on it, and we'll see what we get. So if we take this phi over here, and we sandwich the Hamiltonian in between phi and one of its eigenstates, we have psi sub k, this is going to be equal to ek times the bra acting on. And what is this actually equal to? Well, this is just the phi representation of the state. So this is actually the wave function. So we have, over here, we have the eigenvalue, E sub k, times the wave function as a function of phi. So usually we're used to seeing psi as a function of x. But over here, x is actually phi. This is the coordinate. So this is the phi representation of this eigenstate over here. So we have just the phi representation, and it's exactly the same as the Hamiltonian operator acting on the wave function, and that gives us the eigenvalue multiplying the wave function. So let's write this out in full. What is it actually going to look like? Well, if we write it out in full, we're going to write this Hamiltonian out in full. It's going to look like this. We're going to have 4EC multiplying. So what's going to happen inside here? This is analogous to the momentum. So it's actually going to be a derivative. It's going to be minus I times a derivative with respect to phi. And then we also have this constant, minus ng. And we want to square all of this. Then we want to subtract off Ej times the cosine of phi. But what is the phi operator? What does this phase operator look like in its own representation? Well, it's just phi. It's just like position is the position operator in the position representation. If you act with the position operator in the position representation, you're just multiplying by position. You're multiplying by x. So here we have cosine of phi, and all of this is multiplying the wave function, which is a function of phi, and that's equal to the eigenvalue times this wave function. So have a look at what we have over here. This is the time-independent Schrodinger equation. We have an eigenvalue equation. We've got this complicated differential equation. And you can see that this term over here is analogous to the momentum. This is just like the momentum operator. Usually for the momentum operator, we have h bar over I times the derivative with respect to position. But what has happened to that h bar? Again, we're dealing with dimensionless operators. These guys are dimensionless, so that h bar disappears. That is very convenient, and that is why we chose to define these operators in this way. To get rid of those dimensions, then we don't have to worry about h bars appearing everywhere. So here we have this momentum, which is a derivative, and then we're subtracting off this ng. So what is this actually going to do to this wave function? We have to expand this out, and that's going to give us three separate terms. We're going to get a second derivative, so we're going to have to take a second derivative of this guy. We're also going to have a mixed term, which is just going to have first derivatives, but it's also going to have the imaginary unit I. And then we're going to have this constant squared, and that's just going to multiply this. And what about this? Well, we're just going to be multiplying this function by cosine of phi. So that is how all of these guys are going to act on this wave function. And when we evaluate all of that, that's actually going to be equivalent to just multiplying the wave function by the eigenvalue. So how do we actually solve this? Well, it's a pretty intimidating differential equation. But in the study of differential equations, people have already figured out how to solve general forms of differential equations. And in fact, you can write this as a Matthew differential equation. And the Matthew functions can be used to express the eigenfunctions of this differential operator. So this differential equation has known solutions. And we can actually graph those known solutions as a function of this little shift, of this offset, n sub g. And if we do that, we're going to have the lowest eigenvalue, the E0, E1, and E2, all the excited eigenvalues as well. And they will depend on this ng. And the shape of those graphs are actually going to change depending on the ratio of Ej and Ec. So the ratio of Ej and Ec has very important applications. So I'll write this down. Ej over Ec determines a lot of the shapes of these eigenvalue plots. And if you start off with a system that has comparable energies, where Ej and Ec are roughly equal to each other, that is actually described by the Cooper pair box. So this system describes a Cooper pair box. And then if you keep increasing this ratio more and more and more, you're actually going to get to the quantronium. And the Cooper pair box and the quantronium were qubits that were used before. But what was discovered is that if you keep increasing this ratio more and more and more, up to about 50, so you want this to be about 50 times bigger, Ej needs to be about 50 times bigger than Ec, then you get to the Transmon regime. So for the Transmon, this energy associated with the Josephson junction is much larger than the energy associated with this capacitive term. And that allows us to actually ignore this shift. This little shift but this offset can be ignored because the dependence is very little. What does that physically correspond to? It means there's very little sensitivity to charge noise. And that's exactly what we want. If we're building a device, we don't want there to be sensitivity to noise. We want that to go down. But there's actually a cost. If you keep increasing this, you also lose a bit of anharmonicity. It's also important to have anharmonicity, but you don't want too much sensitivity to noise. So it's a trade-off. But it turns out it's worth it. It is worth increasing this ratio and having it be about 50, and that actually guarantees that you still have a little bit of anharmonicity, but you don't have that intense sensitivity to noise. And this is actually a very practical device. And that's why transmons are very commonly used now in these experimental devices for quantum computation. So I'm actually going to include a GIF that shows a little animation of how those energy eigenvalues change. So the important thing to remember is that this has a known solution. We can find the solution to this differential equation. And the solutions can be written in terms of Matthew functions. And those Matthew functions can be used to plot these wave functions. But what we're really interested in are these eigenvalues, these energy eigenvalues. And they can also be plotted, and they can be plotted as a function of ng. And as you move this ratio higher and higher and higher up to about 50, then you're going to get to the transmon regime. And you actually have very little dependence on this little shift, ng. So that's a very important point to remember. In the next video, what I'm going to do is I'm going to write these guys in terms of ladder operators, these creation and annihilation operators. I'm actually going to find some different forms of the Hamiltonian for the transmon. These are going to be approximate forms, and then I'm going to find the energy spectrum of the transmon using those approximations. So that's going to be in later videos in the quantum mechanics playlist. But for now, what I want you to remember is that we started with the Lagrangian, we took the Legendre transform, that gave us the Hamiltonian, we promoted the operators, we promoted those quantities to operators, and we wrote this in the language of quantum mechanics. Then we looked at some approximations that can be made with the Taylor series. We wrote this in terms of the phase basis, and that gave us this differential equation. And then we talked about the physical applications of this. So make sure you watch the next video in the quantum mechanics playlist. You can find it if you click over here.